On this episode of the podcast, I have with me Balaji Prabhakar. He is the co-founder of Clockwork and a professor of computer science at Stanford University. We're going to be talking about his evolution in dealing with congestion problems. Fantastic background stemming, whether it's data centers or human congestions. Balaji's been dealing with this his whole career and has transitioned from academic backgrounds to co-founder backgrounds and back and forth. Couple of very successful exits. I'm excited to have you on, Balaji, to kind of talk to us about the congestion problems as a whole and some of the specifics of what you're working on now.
Great. Thanks again for having me on the program. Amir, delighted to talk to you and to your listeners. So the theme of my research at Stanford is networks. I mean, that's my topic. And algorithms for managing congestion, algorithms for managing resource usage, that's what I do. It has happened that in the main, the work has always been about data centers or data networks, like internet initially, then data centers, and now cloud. But in between, there was a few years of interlude where I was looking at congestion on roads, trains, just urban congestion. Okay. And the reason that this is sort of, it's probably the most central problem in a network. So after you build a network, the more popular it is, the more congested it gets, and the less utilization people derive from it. The frustration begins to mount. So unless you deal with congestion, the network is not successful. But as you might imagine, success plus congestion, they're always going together. A successful network is a congested network, more or less, and you just have to deal with it. And that's one of the reasons why it's the problem that I've always been looking at. The first and the third startup, the one I'm doing now, is called Clockwork Systems. And the first one was Nova Systems. I'm a co-founder of Clockwork. In Nova, I was actually the guy who did the switch and line card algorithms. And for what became this Cisco's Nexus 5000 switch. And the other major thing I undertook in the first startup was a standardization of a congestion management protocol for data centers. It became an IEEE standard. And so the theme of congestion for large-scale systems, whether standardization efforts or protocols that get deployed. For example, I worked on something called Data Center Transport Control Protocol, DCTCP, that got deployed in Facebook subsequently. And now in this startup, that theme continues, but it's more challenging as an environment because the cloud is more opaque. A data center operator knows what they have in the data center. They can see the switches, they can see the servers. Everything is available for them to interact with, and therefore measurements can be made, wherever it is that they want to sense bottlenecks or congestion. In the cloud, as a user, as a tenant of the cloud, you're isolated from the infrastructure, and that makes it very difficult, very complicated for you to understand, visualize, and address issues. And for me, a pertinent issue has been congestion, which can delay packets, which can cause applications to run slow, which can drop packets, causing timeouts, just basically a ton of frustration that comes from the consequence of congestion and the inability to directly, wrap your hands around it. Yeah, so those are the high-level themes of my work. I can describe more in detail the latter and the more recent stuff I'm doing. But just something quick about the interlude into transportation systems. It came out because I was traveling in Bangalore in 2007, December, and I was stuck in what felt like the mother of all traffic jams. If you've been to India, you might have experienced this. certainly frustratingly just surrounded by an ocean of vehicles. And so wanted to understand and see if we can address urban congestion, whether on roads, trains, like metro systems or city bus systems. And the tool to address this congestion was incentives, is to try and tease people off of peak hour travel. And so that led to successful deployment, initial pilots in Bangalore, India with Infosys, a large company there, and their employees, and then $3 million US DOT grant for looking at the effectiveness of incentive mechanisms for commuters at Stanford University. And a bigger thing, which is still running in Singapore for their metro system, what we called InSync, Incentives for Singapore's Commuters. That started as a 6-month Stanford project. Then a startup that I did to keep that going called Urban Engines with other folks that looked at congestion, looked at data to understand urban movement, urban mobility. And that startup got acquired by Google Maps. And so that's the background, elaborated, but congestion is a common persistent theme.
Awesome. I'd like to invite you to go to Disneyland with me so you can study the congestion of those lines, because I think your background could be applicable. I guess I was just thinking while I was listening to you is you probably go to a lot of places, and when you see, the congestion with humans, your mind must all of a sudden start, tinkering with, they could improve and optimize this queue this way or that way. So it's got to be an interesting experience when you see a little bit of chaos or a long queue someplace.
Yeah, no, it's very natural. It's something, you're right. Actually, it does happen. And I was in Disneyland queues. One thing I've noticed that they do, which I like, is they say if you enter the line now, it's 45 minutes to the front, and so this is nice to let people know. But there are other places where it's just scheduled, so you don't have to wait for 45 minutes in the line. You're given a time, like a boarding pass style thing. Come at this time and it'll be your turn. Meantime, you can go occupy yourself with something else other than just stand in line, which itself can be very frustrating as an experience.
Absolutely. I guess let's to kind of dive into some of what you mentioned in terms of what you're working on, specifically like Clockwork. You're dealing with. You mentioned congestion within cloud infrastructures. I guess maybe talk about why that's a challenge. Maybe if we get a little bit high level of what is the premise of the problem you're solving there?
Well, the idea is this: that is, in a cloud, what happens is I'm sharing resources. I am a tenant in the cloud. I'm some startup, or I'm a large company. For example, a company like Netflix runs out of the cloud. A company like Snap runs out of the cloud. So the users of Netflix and users of Snap all are catered to in the cloud. And or it could be a startup like us, or it could be something bigger than us. Okay, and so we're all using the cloud for computation or other reasons. Okay, so if you look at that, an environment where there are multiple tenants who come and rent resources and use these resources for whatever they want, and leave. Sometimes they could stick around for a year or many years. Like if you're running a shop, for example, Amazon, itself, when you go shopping, it's always in the cloud and it's always running, right? So if you look at systems like that, as a tenant, while you have access to the infrastructure, you lack the ability to know what's happening underneath this sort of level of virtualization. And so what if, in a nutshell, a virtual machine is a bubble that you get a bubble of compute, memory, and some amount of network bandwidth. And that is what you are paying for. And you could pay for multiple of these virtual machines. So it's not uncommon to have something at a minimum of a few virtual machines, let's say single digit, to some large businesses can have easily tens of thousands of virtual machines running, right? Now, no matter which side of the spectrum you are, small or large, you can sense things inside the virtual machine, but you don't know what happens to traffic that leaves the virtual machine. how long did it take to get from A to B? That question seems simple to answer because you left here at some time, arrived there at another time in future, and then you said, look at the difference, and that should be the time you spent in the network. Well, the unfortunate problem is that the clocks here and there may not be synchronized. If they're not synchronized, it's possible that your time of leaving is actually, later than your time of arrival. So you could have negative travel time, which is obviously impossible. Okay, and so as we've squeezed ourselves into these data centers, the time to go from one virtual machine to another is in the order of a few tens of microseconds at most in an unloaded network. And now that can really begin to, be difficult to measure. So historically in networking, we've always taken round trip time, the time to go from here to there and back, as the measure of distance, as a measure of that divided by 2 is how far the sending and receiving nodes are. This is how we've always thought about it. But of course, this conflates forward path and reverse path. It conflates the flip around time of the acknowledgement of the receiver. Too many things are getting, conflated, and it's actually not easy to understand what quality of service you're actually getting. So one of the basic things we did at Stanford circa 2016 was a paper that came out of my co-founder's PhD thesis, Yilong Geng, was an accurate clock sync system over a network, jittery network, like a packet switch network, such as in the cloud or in any data center, at scale, meaning tens of thousands of nodes, and high accuracy, meaning like sub-microsecond accuracy with software timestamps in the cloud. With something like that, now you can start measuring. And the first issue with any problem you want to solve is to be able to measure it, is to be able to say, I think, Kelvin or someone said this, if you can't measure it, you can't fix it. I'm paraphrasing him, but that's really the first step is to be able to measure a phenomenon that you want to understand and address. Okay, and congestion in a modern data center or cloud environment, that's exactly the nature of the beast, is that it needs to be measured, and that had been difficult. Now we can do it. That's not all. We didn't stop there. We didn't want to just measure. We measured, and then we were able to find interesting new ways of controlling congestion, going beyond what we were able to do before. So one of the things that comes as a consequence of this is it has always been thought that in a packet switch network, we will not just utilize the links, but also some of the buffer spaces of the switch. That, if you want to really run the link at a full capacity, you will fluctuate and sometimes take space in the buffers. And then when that happens, you may end up dropping packets. This is just, the cost of doing business on a packet switch network. This is what we've all been dealing with. Except now that we have the ability to measure congestion very accurately and very quickly, we don't have to drop any packets. We can stop just short of overflowing buffers. Okay, so it's a very different, very new style of being able to do things. It's just again possible because of accurate measurement being possible to do. And then of course you can build higher level systems on top of this. Many folks who build databases on many different nodes called distributed databases want to have the clocks of these nodes synchronized so they can offer consistency guarantees. A notable such system is Google's Spanner database, and the clock sync system they use is called TrueTime. It has clocks that are pretty stable. It uses clocks that are stable and guarantees a 7 millisecond accuracy of clocks globally. And it's, of course, available on only some servers in each database, in each region. Whereas what we can do is take conventional clocks and build out of them a system of accurate clocks. Okay, so that's one example. Many other things exist of this consensus protocols, whereas other applications emerge once you have accurate clocks.
I guess, that seems like a very interesting problem, especially in applications, as you were mentioning, that need very refine very accurate, past hundreds or thousands of a millisecond of accuracy. I guess in terms of use cases, and I guess where the problem space is most applicable, what are some of those things?
Yeah. So, I'm going to actually even, if you don't mind me paraphrasing your question, if for 50, 60 years of packet switch networking and distributed systems, we've lived without accurate clocks, how have we done what we have been doing? Okay.
Much better question, actually. I like that. I'm going to go with that one.
Right. So, well, first of all, like I mentioned, my area of research is networks, and we always thought of measuring distance by round trip time and round trip time divided by 2 sort of thing. Even though we know it's inadequate, okay, it's like you make do with what you have, and in that sense, we have tolerated a certain amount of inefficiency. So we've known that we can't really run the links at full capacity or near full capacity without spillage. We've always taken that as a collateral damage of, I'm going to call it ignorant stacks, not knowing what the time is, not knowing precisely what the delay is, or thinking of everything as round trip time divided by 2 and ignoring the actual numbers. We've paid a small tax. We paid a small or a large tax, typically a larger tax than necessary. Okay. We always have 10x bandwidth. Every time we're in danger of overrunning links because the capacity, the utilization is going up, we don't ever dare to run things at anywhere near 80-90% load. We always think of it as 30 to 50% load max. If you look at guys who run financial, exchanges, they don't want to run anything more than 10 to 15% load. So we've significantly over-provisioned. That's been our way of paying ignorance tax. Okay. But it's been okay because we've always managed to 10x the bandwidth. Okay. And so except that as that becomes expensive and it becomes possible that you can actually utilize it close to full without having to pay the penalty or packet drops and delays, well, suddenly it opens a lot of new doors. Okay. So that's one of the immediate applications is that you can, don't have to, you can first make proper measurements. You can get better logging and monitoring systems. You can get better network latency measurement systems. You can get better transport protocols that don't drop packets, that don't cause delays. Okay, the other applications are to the systems I mentioned. I mean, if you have a number of synchronized nodes that are well synchronized, I think the way to put that is, what have we done for the 50, 60 years of distributed systems? Well, the nodes have alternated between 2 states. They work to produce what's called good put, and then either while doing that or taking a break, like in the case of ledgers, like permission ledgers and stuff, work on separately coming up with consensus. Typically, what I mean by when I say consensus or consistency, I mean between some events is a way of ordering the events that have occurred at different nodes in such a way that it's non-conflicting. Okay, so in other words, if I deposit money before withdrawing it, then withdrawal should not occur before deposit because the money wasn't there for me to withdraw. Okay, so to order the event withdraw ahead of the event deposit would be wrong because that would be incompatible with wouldn't be legitimate ordering. Okay. And these two can occur at different machines, and now I need to know how to order them. Because when I interact with the system first time, I went to machine A, second time I went to machine B. I did deposit in machine A, withdraw in machine B, but the timestamps are unsynchronized. So, you have to order them, okay? So ordering systems, which is fundamental to distributed systems. In fact, Leslie Lamport and folks like Barbara Liskov, famous CS folks have worked on this topic in the 70s. And have received, Leslie Lamport recently received a Turing Award as well for pretty much this exact topic, as well as previously Barbara Liskov. So these are sort of fundamental topics which have attracted serious attention, all having to do with what do you do in the world where we don't have clocks. Okay, now that we have clocks, it's like a time to revisit some fundamental beliefs and premises. But the products really they're already out there. Consensus protocols are widely used, like in Kubernetes and stuff, notably a system called Raft, which is also was developed at Stanford, which does something similar to what a system previously was called Paxos, what Lamport developed. Raft is something that came out of Stanford. Now we have a system that we've developed that is 10x or between 10 and 15x faster than Raft because we use accurate clocks. Okay, and Raft is something that underlies systems like Kubernetes, where you store configuration information. So I have a large number of virtual machines or a large number of containers and pods. Where am I? Who's doing what? Right, this configuration stuff. If you lose it, you have now got a large deployment where you don't know what is where, so you can't do things like routing, and it won't function anymore. So you need a secure vault, and that's when you have the systems. Okay, so there's a lot of applications of that type, mostly because it's really fundamental. One application that is outside of the conventional notion of distributed systems is financial trading. So many financial companies are our customers, notably exchanges like NASDAQ and some trading firms. There, the issue is one of fairness. Fairness means when multiple market participants are placing orders, and those orders are going towards the common matching engine, which is executing these orders, what is the temporal order in which you should execute these bids that are being placed? Well, the fair way of doing it is first come, first serve. So if you spot a market event or an opportunity ahead of me, and you place a bid ahead of me, we should be the first one to execute and take advantage of it. It may not happen that way, even though we reacted first. It may not happen that way because the wire that connects you to the matching engine could unfortunately be longer than the wire that connects me to the matching engine. So I went second, but I got there first, and you unfortunately are now unfairly treated. So many, or not many, in fact, all exchanges now take great pains to build fair trading platforms because it's legally required as well as it's demanded by market participants. And that's sort of bespoke data center design is not possible in the cloud, because in the cloud you get virtual machines wherever you get them, and no one's guaranteeing you equidistance or anything like this. But now imagine that if you have an accurate clock system, even though the wires may not be all the same length, and even though I may be able to overtake you to the matching engine, but I have a timestamp that's after your timestamp because my bid was placed second, even though it's placed at a different node, because the nodes are synchronized in time highly accurately. It had a later timestamp than yours. So when I get to the matching engine, it will hold my thing for a certain amount of time, allowing your bid, should one exist, to arrive and take precedence over mine. Okay, that sort of thing. So this is an interesting new use case, different from typical distributed systems. Same thing happens when market data is published. No market participant should be able to read price notifications ahead of anybody else. In a world where wires are different, and how do you guarantee that? Well, you hold and release. You get this market data, close the market participants, make sure adequate time has passed to get everybody's data at the edge, and then release it all simultaneously. So clearly, these hold and release buffers that are available at different parts, they have to be synchronized. So there are many use cases like this. In fact, anything more real time will end up, being in this world of accurate clock sync.
Yeah, it's interesting. Obviously, I drew a trivial analogy, but I actually was thinking about people who were probably on eBay in the last 10, 15, 20 years. And the strategy was, I'm going to wait till the last second and put a bid, and everyone was trying to do similar and put in a similar bid. And now that we're talking about it, depending on how far you were from the necessary node that was taking you to whatever server was settling a last second bid because everyone's trying to get, it closes the auction at, midnight, and you're trying to get in 11:59 and 59 seconds. And guess what? You might have need to do that 11:59 and 57 seconds by the time it got there. So interesting problem because, obviously when it comes to high frequency and trading highly regulated industries, I mean, that makes sense. In normal worlds, I was thinking about my watch. I'm like, I'm thinking, is this really the time? If we were to go out on my Apple Watch to thousandths of a second, what is that an accurate time? Because obviously there's probably some latency in terms of knowing what the real time is. But obviously that's not really what, no one's gonna worry about milliseconds on a watch. But it's interesting about, you mentioned first come, first serve, and then actually the information dissemination. I hadn't even thought about that, but I was thinking people could take advantage of milliseconds depending on algorithmic trading out there and whatnot.
Absolutely, and they do. I mean, there's always arbitrage opportunities available exactly of this type. And I mean, to your point, I mean, it's not like simultaneous release of information is a new problem. I mean, earnings releases for companies, right? There's legal ways of also ensuring you don't open something before an appointed hour, right? So it's sent to you and you're not allowed to open it before a certain appointed hour. There's legal consequences and stuff, right? So that's what you would do in a world where you really care to have it, but you're not really thinking of it at the millisecond level. And so this is a common problem. I mean, people now talk about smart contracts. What that means is a contract where the clauses of the contract can be, functions of factors like time or something else. So what makes them smart is that the conditions may be subject to apply or not dynamically, okay, depending on external circumstances, let's say, okay. I'm simplifying the definition of it, but let's take that for a thing. So it is possible that now I can sell you something or post something on eBay with the condition that this price is only valid between time X and X plus 100 milliseconds. Now, if you're someone trying to react to something like that, what are you supposed to do? I mean, if your clocks aren't synchronized with, wherever it is that this offer is being sold, you have no idea when to go, right? Or you can't work with systems like this. Incidentally, eBay is a customer actually of Clockwork, but that's one example. Many online betting systems are now similar. It has been historically the case that during the course of a game, notoriously, for example, a 5-day cricket match, test match, odds keep changing. During the course of a 5-hour, let's say, Grand Slam final match in tennis, the odds are changing. Fortunes are changing and odds are changing. And if you now go down to what frequency are the odds changing, and now it's important to know when you placed your bet. And you being one of potentially millions of people, now it becomes a really interesting, challenging problem because various different clocks somewhere out there have to be synchronized. And it could be delivered to you through an app that you're supposed to interact with the betting system, through an app. So it's sort of very interesting and challenging. And it also has a very strong consumer flavor as we look into the future, right? And so, yeah, it's a ubiquitous thing. It's anything real time has that quality.
That's super interesting. I've been, it's all, I think the use cases are, just what you mentioned, just a few examples. I think everyone will listen to it and start using their imaginations of when maybe microseconds and milliseconds would have meant something to them. And I guess the previous examples you provided, the human congestion, we're joking about, Disneyland. We've talked about, the packets network switch, that Cisco acquired. Something I've been kind of just thinking about, and I was curious how you view this, and it probably is not a short answer, but I'd like your view. Is you have, I guess, so many places you could apply, solving congestion issues and finding a spot, finding the right problem. That seems to be, that could be a bit of a challenge, because obviously you could solve something too simple that's trivial, something too complicated that can't be used, it might be too theoretical. But how when you're looking at these and you had multiple exits, how do you evaluate what's a good problem set to apply your academic and fundamental understandings of congestion networks?
Yeah, first of all, that's a very good question. It's not an easy one for researchers to answer, mostly because very unexpected use cases emerge. If you go back to the internet sort of pioneers and say, did you think all this? I don't think anybody had the foggiest idea that they would be doing what they did then had this kind of a telling effect on humankind. Okay, but more modestly and more directly to the point of your question, right? So the issue here is if the main thing is if the problem is fundamental. It's fundamental to when resources are shared, that could happen simultaneously. When that happens simultaneously, congestion will show up. Okay, and the more popular something gets and the bigger it gets, the more likely it's going to happen and the more longer it's going to persist. And it doesn't have to be with packets in the network or people on trains and buses. Just think of this summer. One of the things that caught my eye was the baggage issue. People are traveling. Bags are getting, accumulated in these massive warehouses. People don't know what to do, and it's people in the bags are parted, sometimes never to meet. If you hear the horror stories that people had to endure, right? And now that's another opportunity. I mean, how do you think of scheduling these things? How does this work in a time when flights are not exactly running on schedule because of oversubscription, overuse, etc. How do you make sure that people and baggage all get together? The common, destination of interest, right? So that's an example. But I'll give you a funny little example from, everyday common sort of more of a everyday example of a situation where you actually want congestion. Okay, so I was postdoc in England, for 2 years, and there's a strong pub culture in England, as you know, and we would go to this pub in the evening that was by Cambridge called the Eagle. And it's a popular watering hole. And so if you go early, there are lots of people, lots of space, few people. But as the evening progresses, more and more people come in. And it's always a tendency for a group of, let's say, 6 to 8 people to form a circle. And that circle leaves a space open in the middle, which becomes a space that nobody can enter because it's a circle formed by people who are mutually acquainted with each other. Okay? But that's not what the pub guy wants. The guy who runs the pub wants you to, just break that circle because it's taking up too much space. He could have packed more people in. And the trick I noticed they use was they jack up the music, they blast the sound of the music. There's no way now you can hear each other across the circle. So it breaks up the conversations into twos and threes, and you're now shouting each other's ears. On the one hand, it feels like, wow, what atmosphere. On the other hand, it actually is a trick to get more people packed in. Okay. So this is an example of something I wouldn't have thought of observing this if it wasn't my area of research and of interest to me directly, right? So that's another example.
That's awesome. I'm now going to pay attention anytime I go to a place where a bar, a pub, and I'm going to pay attention to the spacing of people. And as the night gets busier, I'm going to pay attention to how loud the music gets and how close I'm going to get to because it's happened now that I'm thinking about it. I'm like, oh my God, that's happened so many times. You're right. You have to literally be shouting in someone's ear, and all of a sudden your space does get much more condensed. Super interesting observation.
Yeah, no, in a post-COVID world, we're all scared of, everybody has physical distance in mind, but just thinking of how practically how this was working was basically that. The music wouldn't be loud until 6:37, and suddenly it gets really loud because the guy's observed that he needs to now start packing people in. So anyway, it's an application of an idea to achieve something, right? Either to congest or to remove congestion.
Yeah, I like it. That's a great story. I appreciate you sharing. I was going to ask you. I mean, you probably have a lot of people at your disposal to answer questions that you would like answered from a technical perspective, but maybe in other areas. Is there something that you'd like a potential future guest or maybe a topic around an episode that you'd like to hear about?
Yeah, no, I think I mean, as someone who works in networks, the way networking people think of what they're doing is understanding and making sense of large-scale complex systems, where the rules are all somehow local, but then the behaviors are global behavior emerges from sort of locally applied rules. In light of the fact that we've had a massive pandemic, and in light of the fact that we're observing more of the consequences of climate change and stuff, when viewed as large-scale complex systems, the spread of diseases, viruses, and the reaction of health authorities and people to that. Some scholarly or someone who can actually make sense of it at a systemic level, because it's taken a long time for us to wrap our heads around the complex ways in which computer networks can behave. And I'm happy to know some things, and as a collective, I think we understand several things. Of course, many things we still don't understand, but things are getting. But it'll be nice to understand something from an epidemiologist, or like with all these wildfires and global sort of climate change things. Somebody who understands this at a systemic level, right, and can explain things. At some point in the evolution of a subject, it is now ready for explanation to lay people, and a person who's in the field is more capable of doing it earlier. So someone like that would be awesome, I think.
No, that'd be fantastic. I think a lot of people probably could benefit from that kind of explanation, because I think we're all dealing with it. I mean, that's a great one. I like it. Hopefully, we'll see if someone who listens can actually chime in and want to talk about something to that effect. And then, Balaji, you've obviously talked about a lot of awesome stuff. What's the best way getting a hold of you if someone wants to pick your brain or talk to you a little bit further about what you've discussed?
Well, my Stanford account is open and it's accessible by the internet. You can just look me up on my email will show up. It's my first name, Balaji at stanford.edu. Balaji at stanford.edu. That's the best way to get a hold of me. LinkedIn is another way, of course.
Awesome. We'll put those in the show notes. Thanks for coming on. Thanks for sharing. Really interesting subject, and I appreciate your time.
Thanks a lot, Amir. Again, really wonderful talking to you, and thanks for hosting me.
Absolutely. That's it for this episode. We'll be back in, different guest, different topic. Until then, I always ask for two things. If you found the podcast interesting, please share it. That's how it grows. And secondly, if someone actually could speak to Balaji's question, I think it's really interesting. I think from what's going on in the world, it'd be awesome to cover a topic like that, and it's broadly applicable. Otherwise, thank you. And until next time, goodbye.